Hello, welcome to Marine Gurukul Online Academy. We are pleased to present this video which shall take you through calculations involving grain stability for ships which are in possession of document of authorization. Let's have a quick recap of stability requirements detailed in grain stability video 1. The angle of heel due to the shift of grain shall not be greater than 12 degrees, or in case of ships constructed on or after 1st January 1994, the angle at which the deck edge is immersed, whichever is lesser. Obviously now, since more than 30 years have passed since this cutoff date became applicable, that is 1st January 1994. So it is unlikely that now you'll be sailing on older ships. So it shall be lesser of 12 degrees or angle of deck immersion. In the statical stability diagram, the net or the residual area between the heeling arm curve and the righting arm curve up to the angle of heel of maximum difference between the ordinates of the two curves, or 40 degrees, or angle of flooding theta 1, whichever is the least of the three, and shall in all conditions of loading be not less than 0.075 meter radians. The initial metacentric height after correction for the free surface effects of liquids in the tanks shall not be less than 0.3 meters. After loading, the master shall ensure the ship is upright before proceeding to sea. The new thing that we have to learn is how do we obtain the volumetric heeling moment of a ship which may be loaded with grain. Why? Because if we recall the lambda 0 formula in video 1, the numerator of that formula was assumed volumetric heeling moment. The grain stability manual on the ship contains the volumetric heeling moment curves as well as volumetric heeling moment tables for all the compartments that may load grain. Sample volumetric heeling moment table is as shown on the screen here. Now these tables and the curves are ship specific, like this one is for Diamond 53, and on the ship also they are compartment specific, like this one is for number 1 cargo hold. These tables can be entered with the height of the cargo or with the ullage of the cargo. Against the height or the ullage, we get the volume of the cargo in the compartment, and the fourth column, which is marked as shifting moment with units m raised to power 4, is the volumetric heeling moment. We shall obtain the volumetric heeling moment of the compartment against the height of the cargo or the ullage of the cargo, and the table will also provide us the LCG of the cargo, the transverse center of gravity location of the cargo, and the vertical center of gravity of the cargo. So here we have a sample volumetric heeling moment table, which besides providing volumetric heeling moments of the compartment, also provides us the volume of the cargo and the vertical, transverse and longitudinal location of the distance of the center of gravity of that particular cargo. From the tables we obtain the calculated volumetric heeling moment. So whatever values you'll get from here in our discussion, we shall be calling it as calculated volumetric heeling moment. Now from the calculated volumetric heeling moment, subject to certain corrections, we shall arrive at what we shall call as total volumetric heeling moment of that particular compartment. So from the calculated volumetric heeling moment of each compartment, we shall arrive at total volumetric heeling moment of each compartment. And the total volumetric heeling moment of each compartment shall be added together to give us the assumed volumetric healing moment of the vessel, which shall be the numerator of the lambda zero expression. If you recall, don't you think it's very similar to how you deal with the free surface in the tanks? You calculate the FSM of each tank and add that together to get the FSM of the ship. So here also you get the total volumetric healing moment of all the compartments where the grain may have been loaded. Add that together and that gives you the assumed volumetric healing moment, which is the numerator of the lambda zero formula. Now, how do we get the total volumetric healing moment for filled compartment trimmed? Now, if you remember, this term filled compartment trimmed was defined in video 1. For the purpose of demonstrating compliance with the stability criteria, that means for the purpose of showing that you are in compliance with the stability criteria as per the grain code, the ship's stability calculation shall normally be based upon, so that is the normal expectation of the organization, that is IMO. The ship's stability calculation shall normally be based upon the assumption that the center of gravity of the cargo in a filled compartment trimmed shall be at the volumetric center of the whole cargo space. Somebody may say if it's filled in, then it has to be the volumetric center. Well, when we declare a compartment filled and trimmed, we make every possible effort to fill it as much as we can. But please appreciate, some voids are inevitable, inescapable. So the IMO does not want, the grain spirit of the grain code does not want you to account for those voids when you consider the kg of the cargo. So if you declare a compartment to be filled trimmed, the grain code wishes that you take the centroid of the full cargo space as the kg of that particular cargo. And if you live by the spirit of the code, then in that case, the total volumetric healing moment of that compartment will be same as what you will obtain from the tables, the calculated transverse healing moment. That means no correction is then required. In other words, can we say it that in that case, the total volumetric healing moment will be 1 into calculated transverse healing moment, because when we multiply by 1, there is no change in the value. In those cases where the administration authorizes, now number 1, whatever we are going to now understand is subject to authorization of the administration. It's not the birthright of a ship owner or the ship owner's representative. So in those cases where the administration authorizes, account to be taken of the effect of assumed underdeck voids. So those voids which were inescapable, if you want to say no, there's no cargo, the center of gravity should be lowered. So in those cases where the administration authorizes account to be taken on the effect of assumed underdeck voids on the vertical position of center of gravity of the cargo in a compartment declared filled trimmed, it will be necessary to compensate for the adverse effect of vertical shift of grain surfaces by increasing the assumed healing moment due to the transverse shift of grain as follows. That means now you have a compartment which is declared as filled trimmed, but now you want to, with the authorization of your administration, you want to use a lower kg of the cargo instead of using the centroid of the space. In that case, the total volumetric healing moment of that compartment will be equal to 1.06 into calculated transverse healing moment. So whatever you obtain from the tables will have to be increased by 6%. So if you're trying to lower the kg of the ship by playing around and leaving out the voids and compensating for the voids on top, then since you are trying to show enhanced stability by lowering the kg of the ship, same will be offset. Why? Because now your numerator of the lambda 0 expression will go high, and therefore they are saying in such cases the total healing moment should be 1.06 into calculated transverse healing moment. Remember, calculated transverse healing moment is what you obtain from the tables. In all cases, the weight of a filled compartment trimmed, weight of the cargo in the filled compartment trim shall be the total volume of the compartment, not the actual volume of the cargo. It will be the total volume of the compartment divided by the stowage factor of the cargo. How do we deal with filled compartment untrimmed, which was again defined in video 1? In a filled compartment untrimmed, the center of gravity shall be taken at the volumetric center of the whole cargo compartment, and there is no account being allowed for any void. So that means there is no relaxation. If your compartment is filled compartment but untrimmed, then the center of gravity of that cargo will always have to be taken at the centroid of the space. The weight of the cargo shall be the volume of the cargo. Now this is the actual volume of the cargo, not the full volume of the space. So the weight of the cargo shall be the volume of the cargo divided by stowage factor. Remember, in case of filled compartment trimmed, a while back we said the weight has to be taken as the full volume of the compartment divided by stowage factor. But here what are we saying? The weight of the cargo shall be the actual volume of the cargo divided by stowage factor. The assumptions in the grain code for calculation of transverse healing moment are different for compartments which are filled, trimmed, and the compartments which are filled, untrimmed. So the formulae, the assumptions for calculations are different for filled compartment trimmed and filled compartment untrimmed. How do we get the total volumetric healing moment of a compartment if it's partly filled? In partly filled compartments, the adverse effect of vertical shift of grain shall be taken into account by increasing the calculated volumetric healing moment by 12%. So in such cases, the total volumetric healing moment shall be equal to 1.12 into the calculated transverse healing moment. So whatever you obtain from the tables for partly filled compartments, you need to increase it by 12%, and to achieve that you can multiply that value by 1.12. Before we proceed further, let's have a simplified review of what we learned over last few minutes. That is how to obtain total volumetric healing moment from the calculated volumetric healing moment. In a filled compartment trimmed, if the centroid of the cargo hold or the cargo space, that is the kg of the space, is used in calculating the kg of the ship, which is actually the spirit of the code, then the calculated volumetric healing moment obtained from the VHM tables need no correction. In such cases, total healing moment or total volumetric healing moment will be equal to the calculated healing moment multiplied by 1. In those cases where under the authorization of the administration, in filled compartments trimmed, the actual kg of the cargo is used and not the kg of the space, then the calculated volumetric healing moment needs to be increased by 6%. That means the total volumetric healing moment in such cases shall be 1.06 into calculated volumetric healing moment. In partly filled compartments, the calculated volumetric healing moment of the compartment needs to be increased by 12%. That means in such cases, the total volumetric healing moment will be equal to 1.12 into the calculated transverse healing moment. Let's try to apply what we have learned to a numerical or a question. MV hinge ship displacing 18529 tons, kg 7.539 meters, FSM 1556 ton meter is loaded with grain cargo of stowage factor 1.78 cubic meters per ton. The grain is loaded in the lower holds and twin decks as detailed, with each twin deck completely sealed and made grain tight from its respective lower hold. So each compartment stability has to be dealt with independently. While number 1 lower hold, 1 twin deck, 2 lower hold, 4 lower hold, 4 twin deck and 5 lower hold are filled, trimmed. 2 twin deck and 3 lower hold are partly filled. And number 3 twin deck and number 5 twin deck are empty. In calculating the kg of the ship, kg of the compartments 1 lower hold, 2 lower hold, 4 lower hold and 4 twin deck are used. For compartments 1 twin deck and 5 lower hold, the kg of the cargo was used. If the calculated volumetric healing moments of number 1 lower hold, number 1 twin deck, 2 lower hold, 2 twin deck, 3 lower hold, 3 twin deck, 4 lower hold, 4 twin deck and 5 lower hold, 5 twin deck are as given in the question here, confirm if the vessel is complying with the stability criteria as per the grain code, angle of flooding given as 38 degrees. Now, since MV hinge ship stability booklet is not a grain stability booklet, therefore the calculated VHM of the compartments is provided in the question. Kindly appreciate it's a very hypothetical question. Why? Because we have tried covering all possible aspects here. Otherwise, in a ship, when the compartment is filled, trimmed, it's usually the center of gravity of the space which is used as the center of gravity of the cargo. Otherwise also, even if the voids are to be factored in, then same concept applies to all the holds. What we have done, all compartments rather. What we have done here is, in some filled compartments trimmed, center of gravity of the space is taken. In the others, it's the center of gravity of the cargo is taken, just to clear the concept. So it's a hypothetical question. This will not be the situation on board. On board for filled trimmed compartments, for all the compartments, either it will be the centroid of the space or the centroid of the center of gravity of the cargo. Let's start with carrying out a check on initial metacentric height. Here are the hydrostatic particulars of MV hinge ship. Against the given displacement of 18529 tons, we interpolate km and we get the km as 8.349 meters. Kg of the vessel is given in the question, 7.539 meters. This takes us to GM solid, which is 0.810 meters. We have the FSM and displacement. We can calculate the FSC. FSC is 0.084 meters. giving us the GM fluid, initial metacentric height fluid. That means initial metacentric height after allowing for the free surface effect of the tanks. GM fluid is 0.726 meters. What is the grain code requirement? Initial metacentric height is not to be less than 0.3 meters. In our case, it's 0.726 meters, and hence the vessel is in compliance of this particular criteria. Now we shall use the information in the question to calculate the assumed volumetric healing moment and then calculate lambda 0 and lambda 40. For assumed volumetric healing moment, since the question looks little complex, we can use a table like this if we so desire. Compartment, calculated volumetric healing moment, which in this case is given in the question. The correction factor. Now this terminology does not exist in the crane code. What does it mean? How do we convert calculated volumetric healing moment to total volumetric healing moment of that compartment? And now we have all these compartments in MV Hinship, and we have the calculated volumetric healing moment being documented from this part of the question. They are all given in the question here. So they get captured under the calculated volumetric healing moment. Please pay attention. VHM units are meter raised to power 4. Now correction factor. Now there are some compartments here which are empty. You can see here number 3 twin deck and number 5 twin deck are empty. That means they will have no contribution to the assumed volumetric healing moment. So can we multiply them with a factor of 0? You see 3 twin deck and 5 twin deck, we have filled in a correction factor of 0. So when we'll multiply the calculated volumetric healing moment with 0, the total volumetric healing moment will automatically become 0 for these compartments. Then we have two compartments which are partly filled, 2 twin deck and 3 lower hold. For partly filled compartments, we need to increase the calculated volumetric healing moment by 12%. That means we multiply by 1.12. So you can see for 2 twin deck and 3 lower hold, we have this factor of 1.12. The remaining compartments are filled, trimmed. But in the cases in these questions, in case of these two questions, for compartments 1 twin deck and 5 lower hold, kg of the cargo was used. 1 twin deck and 5 lower hold are filled, trimmed, but kg of the cargo is used. So the calculated volumetric healing moment will have to be increased by 6%. So factor for 1 twin deck is 1.06 and so is for 5 lower hold 1.06. All the other compartments are filled, trimmed, and the kg of the compartment or the centroid of the compartment is used for calculating the kg of the ship. Thus, in all the remaining ones, there is no correction of the calculated volumetric healing moment required. So the factor becomes 1 for all the remaining spaces. Now multiplying the column of calculated volumetric healing moment with the respective correction factor, we can get the total volumetric healing moment of each compartment. Now we can sum up the last compartment, and that becomes the assumed volumetric healing moment of the vessel, which is 4695.5 meter raised to power 4. So this table actually simplifies the problem. Otherwise you can do it in separate steps, but it's your choice as long as you get the correct AVHM. Now we have the displacement, we have the stowage factor, we have the AVHM. We can now calculate lambda 0. This formula was covered in video 1. Assumed volumetric healing moment divided by stowage factor and the displacement. We use these values and we get lambda 0 as 0.142 meters. Having got lambda 0, we also calculate lambda 40, which is always 0.8 times of lambda 0. and we get lambda 40 as 0.114 meters. Next, we need to draw the curve of statical stability or the GZ curve. And let's have a quick recap of the process which you are already aware of. GZ is equal to Kn minus Kg sine theta. Which Kg is this? Kg used in this formula is called as corrected Kg or Kg fluid. What is Kg fluid or corrected Kg? It is the Kg plus FSC. Kn values are obtained from the cross curves of stability of the ship, and they are provided in the ship stability booklet. Kn tables for MV hinge ship are provided on page 21 and 22 of the booklet, and the page looks somewhat like this. You need to enter these tables with displacement in the first column. You have the angle of heel on top here, and then you obtain the value of the Kn against the displacement at different angles of heel, and then obtain the GZ. And once GZ values are obtained, then we are good to draw the GZ curve. Let's now calculate the GZ values. We have given displacement 18529 tons, kg 7.539, FSC 0.084. We add to that, and that gives us the corrected kg or kg fluid 7.623. It is 7.623 meter kg that shall be used in obtaining the GZ. Now, then we make a table like this. We have the heel, angle of heel here on top. Then we'll have the Kn coming from the Kn tables. Kg sine theta. Theta is the angle of heel, and kg is 7.623. And by subtracting kg sine theta from Kn, we'll be able to get the GZ values. Here are the Kn curves. I have uploaded this in the free study material. The MV hinge ship stability booklet soft copy is uploaded. So those who are going to practice it can refer to the booklet in the free study material on the app. Now, the displacement will fall here in this range, and against the displacement for different angles of heel, we interpolate, we obtain the value of Kn rounded off to 3 decimal places, and you can see these values are being now tabulated. So you can practice calculating them, and you can tabulate them like this here. Once you obtain Kn, then kg 7.623 into sine of the respective angle of heel, and we can keep subtracting it from the Kn values and keep filling up, obtaining the GZ values like this. Like this one is kg 7.623 into sine of 15 degrees 1.973, subtract from 2.252, and you'll get the GZ. And likewise we complete this table and we get the GZ values, which shall be used for drawing the GZ curve or curve of statical stability. Now we shall obtain the angle of heel due to assumed shift of grain, for which we'll draw the GZ curve. We have the angle of heel on the x-axis. We have GZ in meters on the y-axis. We calibrate the x-axis, use as large a scale as possible, and then accordingly, based on values of our GZ, we calibrate the y-axis, and once the x-axis and y-axis are calibrated, we plot the values of GZ as in the GZ table, including 0 degrees angle of heel. We plot these values of GZ. We have learned this already, how to draw the GZ curve. And once we have plotted these values, we can join them with a freehand curve and we get the GZ curve. Once you get the GZ curve for the question, then on the GZ scale, we'll plot lambda 0 at 0 degrees angle of heel. And we had calculated this red line here, you see, it is lambda 0, which was calculated to be 0.142 meters. At 40 degrees, we'll plot lambda 40 using the same GZ scale, which was 0.114 meters. Now, with a scale straight line will join the top of these two lines, and this red slanting line that we have obtained here is the healing arm curve, and this one is a writing arm curve, and wherever the two intersect, they intersect here. This point of intersection, the angle of heel for this point of intersection, which is 7.4 degrees, is the angle of heel due to assumed grain shift. What is the requirement of the code? Requirement is angle of heel due to grain shift shall not be greater than 12 degrees. In our case, this angle is 7.4 degrees, and therefore this criteria is also satisfied. Now we carry out a check on the residual or the net area. This is the GZ curve, the writing arm curve, and the healing arm curve that we have drawn. Now we have to calculate this area from here between these two curves up to the least of the three options. Three options are 40 degrees, angle of flooding, which is 38 degrees in this question, and angle of maximum separation of the ordinates between these two curves. Now, if you see the separation between writing arm and healing arm curve, the spacing between them is continuously opening up to 40 degrees. So it's not happening, the maximum separation is not happening before 40 degrees. So that means angle of heel of maximum separation of the ordinates of the two curves is definitely not less than 40 degrees. Second option is 40 degrees itself. And the third is angle of flooding, which is 38. So that means we have to calculate the residual area up to 38 degrees. This is the area we have to calculate from where? From 7.4 to 38. I have used Simpson's rule 2. In Simpson's rule 2, we have minimum 4 ordinates or 3 intervals over this span from 38 degrees to 7.4 degrees. Now, what will be the common interval? There will be 3 intervals over what range? Over 38 minus 7.4 by 3. That means each common interval shall be 10.2 degrees. Now, we at 10.2 degrees each, we mark off this is 7.4. We add 10.2 to it. We reach 17.6. This will be the ordinate here. We add another 10.2 to it. This will be the third ordinate, and this will be the fourth ordinate. The ordinates that we'll need for calculating areas are now highlighted with the red arrows. You can use the same way in your calculations. You can draw them with a straight line. Now, how do we measure these ordinates? There can be different ways of obtaining it. The simplest is, please carry the small divider which you use in the school geometry box. Which divider? I'm talking of this divider, the fine tip divider. Now, then, if you want to measure this ordinate, open your divider from this end of the arrow to this end of the arrow. And now carry the divider, place it at 0 and read off on the GZ scale. Open from this end of the arrow to this end of the arrow, carry it, place at 0 and read off the value on the GZ scale. So now, if you read these the way I have explained, then these ordinates are found to be 0.180, 0.379 and 0.480. So now we have 4 ordinates, 0, 0.180, 0.379 and 0.480. We can now calculate the area using Simpson's rule 2. Simpson's multipliers will be 1331. This will give us product of area. We add this up and we get SOP area. Once we have SOP area, now we calculate this area. Coefficient is 3 by 8. and common interval is 10.2 degrees, which can be converted to radians by dividing by 57.3 degrees. So the residual area is 3 by 8, the coefficient for roll 2. 10 by 2 divided by 57.3 is the common interval in radians, and this is the SOP area. This will give us the area in meter radians. Now, what is the requirement? The requirement is that the net area or the residual area between the writing arm curve and the healing arm curve shall not be less than 0.075 meter radian, and in our case this requirement is also satisfied. So to sum up the answer, angle of heel due to grain shift criteria satisfied. Residual area between writing arm and healing arm curves satisfied. Initial metacentric height criteria satisfied. Master shall ensure that the vessel is upright before proceeding to sea. Let's have a look at exam question. It is from MMD Naval Architecture exam January 2022. A vessel laden with grain in bulk of stowage factor 1.20 cubic meters per ton has a displacement of 88,000 tons. Her kg calculated assuming the centers of gravity of the cargoes in the filled compartments to be at the volumetric centroid of those compartments is 10.30 meters, FSM 2650 ton meter, km 13 meters. The VHM of the filled holds is 5800 meter raised to power 4, and that of partly filled holds is 14,500 meter raised to power 4. The Kn values for her displacement are as follows. Against the angle of heel, 12 degrees, 15 degrees, 30 degrees, 40 degrees and 45 degrees, Kn values are given. Ascertain whether she satisfies the intact stability criteria for vessels laden with grain in bulk. Angle of flooding is 41 degrees. Angle of heel having maximum difference between writing and healing arm curves is 46 degrees. Now this is a question from the exams. Now first let's carry out a check on the initial metacentric height. Km is given in the question 13 meters. Kg is given in the question 10.300 meters. That gives us GM solid. FSM and displacement are given. They give us the FSC. FSC is 0.030 meters. GM fluid 2.670 meters. Requirement of the code is that initial metacentric height is not to be less than 0.3 meters, which in this case is much more. Therefore, this criteria is satisfied. Let us now calculate lambda 0 and lambda 40. Volumetric healing moment of filled trimmed holds is 5,800 meter raised to power 4. The total volumetric healing moment for these holds shall remain unchanged. That is 5,800 meter raised to power 4. Why? Because the center of gravity of the cargo hold or the compartment is used in calculating the kg of the ship. Then we have volumetric healing moment of partly filled compartments, 14,500 meter raised to power 4. This needs to be increased by 12%. So the total volumetric healing moment of partly filled compartments will be 14,500 into 1.12, that is 16,240 meter raised to power 4. When we add these two, we get the assumed volumetric healing moment of the vessel, 22,040 meter raised to power 4. Now we can calculate lambda 0, and lambda 0 is 0.209 meters. Having got lambda 0, we can get lambda 40 now, which is 0.8 times. It's equal to 0.167 meters. Now we calculate the GZ values. kg 10.3, FSC 0.030. We add them, we get corrected kg or kg fluid. This 10.330 meter corrected kg will be used for getting the GZ values. Now we have the Kn values given in the question for whatever degrees they are given is tabulated here. We additionally add 0 degrees here. Kn for 0 degrees in upright condition is always 0. So using the given Kn values, we apply kg sine theta and get the values of Gz. I'm sure every one of you can now get the values of Gz. We shall now draw the Gz curve and get the angle of heel due to shift of grain. We again used as big a scale as possible on the heel and GZ axis. We calibrate the x-axis and we calibrate the y-axis depending on the range of GZ that is required and the angle of heel that we need to plot. So whereas I have been able to expand my x-axis scale because I have to draw only up to 45 degrees, I had to condense the GZ scale because my GZ values have to be plotted up to 2 meters in this case. We plot the given values and join them with a freehand curve and we get the GZ curve here. Now at 0 degrees we plot lambda 0 using the GZ scale. At 40 degrees we plot lambda 40. We join them with a straight line. It intersects the writing arm curve, the healing arm curve and the writing arm curve intersect at 8 degrees angle of heel. So 8 degrees is the angle of heel due to shift of grain. What is the code requirement? Angle of heel due to grain shift shall not be greater than 12 degrees. This criteria is also satisfied. Now we calculate the residual area between 8 degrees and lesser of angle of flooding, which is given in the question, angle of maximum separation between the ordinates of the two, which is given in the question, and 40 degrees. If we compare all the three, we get 40 as the least value. This is the area that we have to calculate. I have used rule 1 this time. So between 8 and 40, we can have one more ordinate and we get the common interval in this case. The common interval will be 16 degrees. And we have these blue arrows representing the three ordinates now. They can be measured again using the same divider which has already been explained. And we get these values. See, at the value for 40 degrees can also be obtained by subtracting from the GZ at 40 degrees, you can subtract lambda 40. So instead of measuring it, if you have 40 degrees, you can exactly get the value. We get these values, we apply rule 141. Coefficient for rule 1 is 1 by 3 and common interval is 16. We calculate this area and we get it as 0.631 meter radian. Requirement is this area shall not be less than 0.075 meter radian. This criteria is also satisfied. So for this question, criteria for angle of heel due to grain shift satisfied, residual area criteria satisfied, initial metacentric height criteria satisfied, master shall ensure the vessel is upright before proceeding to sea. There are some more questions here from past papers. You can pause the video and take a picture of this and solve them and practice. With this, we come to end of this video. Hope you like it. If so, please like it, subscribe the channel, share it with your friends. Also download our app. Our app is intended to provide you a single stop solution for all your academic needs. So please download the app. Thank you very much for watching Marine Gurukul video series.